Hello, we at Whole Heart strive to create a balloon catheter system HH4 that is designed to improve mechanical control, biocompatibility, and minimize the risk of complications associated with the balloon atrioseptostomy procedure for treating patients with transposition of the great arteries. Our team consists of Lauren Baker, Kayla Charles, Vernon Komarninsky, Haley Strauss, and Bryson Whitman, with clinical mentor Sarah Belko and technical mentor Dr. Nika.
So the current problem and solution that our team is faced with deals with transposition of the great arteries, and this is a congenital birth defect that affects 4.7 newborns in every 1,000 born, representing 5 to 8% of heart defects. The current solution for the transposition of the great arteries is to either perform a risky surgery to switch the arteries immediately, or use a balloon catheter system to enlarge the foramen ovale in order to increase oxygen saturation in the newborn prior to the corrective procedure of the repositioning of the great arteries.
The current balloon catheters that are listed on the market include balloon catheter systems that are large in profile, have rigid balloon deformation, and an unmarked catheter tip. With other competitors, they were unable to get their balloon catheter system to be low profile and lacked the ability to create a larger tear in the heart, such as our device, which contains multiple balloons.
To initiate our verification and validation testing of the overall balloon catheter, we started with a generic black box approach that was then split into 5 different parts using the equations found to the left. We then delved further into these using both physical and virtual testing methods. An example of our prototyping activities includes a 3-point bending test to test for the rigidity of the catheter tube. This has a very clear rejection criteria of 0.2 times the span length. So the governing equation to the top left, you can see that's affected by two things, both the force applied and the material characteristics of the property. So since the SolidWorks model and the physical prototyping did differ, these testing strategies were compared as well. In SolidWorks, a range of forces was applied to the middle of the catheter tube for each material of interest, with the measured deflection recorded. Virtual simulations were done. These deflections were then placed into a virtual simulator with applicable standard deviations to run extraneous trials. So the output was then tabulated with green representing those values that fall within the acceptance criteria. With just 3-point bending, nylon was the best material for the catheter tube. It could stay within that acceptance criteria under even the largest of forces. However, with all other prototyping activities, we found that polyethylene terephthalate is actually the best material for the tube, while nylon is the best for the balloons.
The HH4 atrioseptostomy catheter consists of a 4-French low-profile body with multiple radiopaque markers for improved visibility. The multi-balloon design gradually expands the foramen ovale, which eliminates the need for multiple passes to achieve the desired defect size and allows for optimal oxygen saturation.
This device will fall under a Class 2 medical device and will require a pre-market notification. This device market segment falls into the cardiovascular and pediatric market segment with a 6.5% and 8.9% CAGR, respectively.
The manufacturing cost for the HH4 catheter is approximately $533. The selling price of the catheter will be $1,200, which is equivalent to competitor pricing. With equivalent cost and improved efficiency, the device will be reimbursable.
Thank you to all of upper management and our clinical and technical mentors who have aided us in the creation of this medical device.